I expect you're wondering why we're in these unusual surroundings rather than the usual studio. Well, this is the Oxford Regional Office. And we've come here because this week we're not going to do any new mathematics. What we're going to do is look at some problems that crop up when you're doing assignments. And so what we've done is to ask some students to have a shot at the problem in this week's television notes. You know, the one to do with dividing a circle up into 3 equal parts. Well, the staff tutors for this region, Bob Coates and Derek Goldray, have been having a look at some of the solutions that have been sent in. Let's see how they've been getting on.
Must do, yeah. And I suppose that really, once they get on to second level, if they still can't start at the beginning and end at the end, then we're in absolute terrible trouble.
Oh, I reckon so, yes.
Well, I hope by now you've had a good look at the question in the TV notes. It's fairly typical of an end-of-block TMA question. You'll have noticed it comes in quite a few parts. And that's not to make it more difficult. In fact, it's designed to take you step by step through to the end. But even though it comes in parts, it's always best to read the whole question through before you start to get an idea what's going on. Perhaps I should remind you about it by using this ashtray here. You see, we start off by being given a circle, and then we put a chord across it. And the idea is to find the position of that chord so that the area which is cut off turns out to be a third of the area of the circle. Well, let's actually look at the first part of the question. You see, we're asked to use a standard trig formula to prove the expression sine theta over 2 cos theta over 2 is equal to a half sine theta. Well, Derek and I have got quite a few student scripts here, so I'm going to kick off by looking at this one. You see, what this student has done in the first line is to take the expression that he was supposed to prove. He then lets theta over 2 equal to alpha, which is of course the same as theta equals 2 alpha. Makes this substitution and gets sine alpha cos alpha equals a half sine 2 alpha. And lastly, he multiplies across by 2 to get 2 sine alpha cos alpha equals sine 2 alpha. And then he indicates that he's finished. Now, he does that presumably because he recognizes that last formula. It's a standard one. It was actually given in the unit. Well, would I regard this as an ideal solution? Almost, but not quite. You see, this student started off by assuming the result he was supposed to prove. When you're supposed to prove something, that's the thing that ends up in the last line and not the first. What he should have done was to take his standard formula here as his first line, and in the last line end up with the result we were supposed to prove. Well, how many marks would I award this? Well, I'm, as a tutor, not in a position to make that decision. I've got to follow the mark scheme which is given to me in these tutor notes. And I see for this particular sort of solution, I must give it 1 out of the 2 possible marks that were awarded for it. Well, Derek, have you got a better solution?
Yeah, I've got a good one here. Now, what this lady has done is to start off with a standard trig formula from the unit. And there's a nice touch where she's told me what page the formula is written on. That's a great help. Now she's substituted alpha for beta and has got down to the formula sine 2 alpha equals 2 sine alpha cos alpha. Next, she's substituted theta for 2 alpha and has arrived at the result. Now, that's a perfectly good answer and gets full marks. But I've only got one small comment on the script, which is that she could have started her argument with this line here. You see, sine 2 alpha equals 2 sine alpha cos alpha is also a standard trig formula, and it's a perfectly good place to start.
Yeah, I suppose it's sometimes difficult knowing which standard formula to start from. But in principle, the thing is that if a formula appears in the unit, then it's an acceptable starting point. And if you're in doubt, and if you've got time, then you can always do what that student did and start a little further back. And of course, for the exam, the standard formulae will be in the handbook. Well, let's look at the next part of the question. It asks you to find the area of the big triangle AOB. Let's look at this student's script here. You see, he's done exactly what he was asked to do and found the area of the triangle AOD using the hint in the question that it's a half the base times the perpendicular height. He's then found the area of the triangle BOD. And here in the next line, he's realised that the area of the big triangle is the sum of the areas of the two he's just found. And he writes his answer in this last line as a half OD times AD plus DB. Now, that part of the question was worth 4 marks. But if you read it very carefully, it asks you for the area of the triangle AOB in terms of x. And this student didn't do that. Well, fortunately, in terms of marking, this one presents no problem, because in fact, in part 2b, he starts off by showing that OD is equal to 1, that's the radius OA, times cos x over 2, and similarly gets that AD is sine x over 2, and DB is sine x over 2. And here, on the last line of the page, he actually substitutes those values in the formula he found for the area of the triangle. So, in fact, I can give him full marks for part 2a. But the warning is, always read the questions very carefully and actually answer the question as asked, part by part. You won't always be as lucky as this student was.
Well, let's have a look at a correct answer to this part of the question. What this student has done is to say that the area of the triangle AOD is equal to half the length AD times the length OD. And straight away he's put these lengths in terms of x to get a half sine x over 2 cos x over 2. Now he's observed that the area of AOB is twice the area of AOD, and that's sine x over 2 cos x over 2. Well, good solution and full marks. Well, let's move straight on to part B. Now, part B asks us to show that x satisfies the equation x minus sine x minus 2 pi by 3 equals 0. And there's that hint about the area of the sector AOB. Well, I've got a good answer to this one. Let's have a look at it. Now, what this student has done is to notice that the area of the shaded portion of his diagram is equal to the area of the sector minus the area of the triangle AOB. Well, the area of the sector is x over 2, using the hint given at the end of the question. When we give you a hint in a question, then by and large you'll find it useful in your answer. Well, the area of the triangle AOB is worked that out in part A to be sine x over 2 cos x over 2. And then is replaced this straight away by a half sine x. That's using the result of part 1. That's something else about these long questions with lots of parts. When you're asked to prove a result at the very beginning of a question like that, then the chances are that you'll be using the result somewhere later on. And in our question, we're using part 1 right here. Now, to finish off his equation, the student needs to know what the area of the shaded portion is. Well, it's a third of the area of the circle, so it's a third pi r squared, but the radius r is 1, so it's just a third pi. Well, that gives the student this equation. And now multiplying each side by 2 and simplifying gives us the equation x minus sine x minus 2 pi by 3 equals 0, which is just what you're asked for.
Well, before we leave part 2b, I'd like you to look at this script I've got in front of me, because it took me ages to puzzle out exactly what this student was trying to do. In the first line, he takes the expression that he's trying to prove, and then he rearranges it to give x is equal to sine x plus 2 pi over 3. Then he takes this value of x and substitutes it into the left-hand side of the original equation. And then, unfortunately, he manages to get totally lost. Well, I wonder if you've got any idea what he was up to. I didn't really understand it until I looked at this comment he'd written below. He says, "I think this ought to be 0, but I can't see why." And then I knew what he was up to. You see, the question is worded, "Show that x satisfies." I'm sure you'll have seen wording like that before. We might have said, "Show that x equals 1 satisfies the equation x squared minus 2x plus 1 equals 0. And what would we have expected? Well, we'd have expected you to take x, put it equal to 1 in the left-hand side of the equation, and show it was equal to 0. Now, this question has the same wording, but it doesn't mean the same thing. What it means in this case is find the equation which x satisfies, and the answer should be the one given in the question. So here's the moral. When you see show that x satisfies and then some expression in x, it might mean one of two possible things. Either we've given you a value of x, which you're to substitute in and show that it satisfies, or you're to prove that that is the equation which x satisfies. And if it is this second case, as it was here, then, like as not, the previous parts of the question will all lead up to there. Well, before we leave part 2b, let's look again at this script of the student who got totally messed up. You see, in the next part, 3a, what he did, he realised that he could go straight on using the result of 2b, even though he hadn't managed to prove it. And here you see him using that result. In fact, I've looked through this script, and he got everything from here on totally correct. So there you are. If you can't do one particular part of a question, then there's no reason why you shouldn't be able to go straight on and get the rest of the question entirely correct. Derek, you got anything interesting for part 3?
Yes, well, let's look at the question. Now, we've got an equation for x in the last part, and in part 3, you're asked to find an approximation for the value of x, which satisfies it. And you're given a function f with the rule which sends x to x minus sine x minus 2 pi by 3. In part A, you're asked to calculate f of x for a number of values of x. And then in parts B and C, you're asked to solve the equation f of x equals 0 by locating an interval in which a solution lies and then finding it by the bisection method. Well, let's look at some answers to part A. Now, what this student has done is written down the rule for f, and now he's got f of 0 equals minus 2.094. Well, I'll have to check that answer up on my mark scheme, and it agrees. Now, for f of pi by 6, the student has got minus 1.580. But the mark scheme has got minus 2.071. So maybe the student's made a slip there. Well, let's look at another value. F of pi by 3, the student's answer is minus 1.065, but the mark scheme gives minus 1.913. And in fact, the student's answers disagree with the mark scheme all the way down. So, what's gone wrong? Has the student made a mistake, or perhaps the mark scheme is wrong? Well, there are lots of possibilities here, but I think I know what happened. And I'd like to test my hunch by seeing if I can reproduce the student's answer for f of pi by 3, which was minus 1.065. Well, see if you can spot my deliberate mistake. Right, well, I'll switch the machine on, enter pi, divides 3 equals. Well, that's given us pi by 3. And now we want to subtract sine of pi by 3. And on my machine, I can do that by pressing subtract, then sine. That's given sine of pi by 3. And now equals gives pi by 3 minus sine of pi by 3. Now, lastly, we want to subtract 2 pi by 3. So I press subtract 2 times pi divides 3 equals. And get the answer minus 1.065. That's to 3 decimal places. So, was the student right after all? Or did you spot my deliberate mistake? Well, my mistake was to leave my machine working in degrees. You see, on this machine, you have to make a positive decision to work out sine x in radians. And in fact, if I'd done that, then my key sequence would have given the right answer. Well, the student's gone on to answer the rest of the question, and the tutor notes tell me that I can follow his mistake through. But even if his method is absolutely correct later on, he won't get full marks. So, when you're answering a question that involves the calculation of trig ratios, make absolutely certain you're working in the correct mode. And most of the time, that means radians.
Well, if you've got a pencil handy, then before we go on to the answers to part 3, you might like to jot down what the correct function values are. I've got a student here who has the correct answers on the script, so let me read them out for you. F of 0 is minus 2.094. Then we get minus 2.071, minus 1.913, minus 1.524, minus 0.866, 0.024, and lastly, f of pi is 1.047. Well, this student goes straight on and says f of x equals 0, in other words, f of x equals 0 has a solution in the interval 2 pi over 3 to 5 pi over 6. And there's a very nice diagram to illustrate this, because you see the value at 2 pi over 3 is negative, whereas the value at 5 pi over 6 is positive. And if you join these up with a curve, then somewhere in between, the function crosses the x-axis. In other words, the function must be 0. And that's exactly what we mean by f of x equal to 0 having a root. Well, full marks for that.
Okay, let's look at this solution to part C. Now, straight away, I can see that the solution produces the wrong answer. And if I look back up the table, it seems to have got too many lines. Now, I know from the tutor notes that fewer cycles of the bisection method are actually needed. So, what's gone wrong? Well, the student's got the right starting interval in part B, and his first approximation, x1, ought to be midway between 2 pi by 3 and 5 pi by 6, and in fact it is 2.356 to 3 places of decimals. Now, the value of the expression for x1, that's correct as well, but the maximum error is wrong. See, the maximum error ought to be half the length of this interval. And that's a half of roughly 0.5, so the maximum error here ought to be something like 0.25. And that, in fact, explains why the students used too many cycles of the method. Well, then there's x2. Now, this answer, this second approximation, is totally wrong. And the trouble with the student's answer is he doesn't give me enough information in his table to judge why he's gone wrong. In fact, when he looks at his script again, for instance, if he's revising for the exam, I don't think he'll be able to understand what he's done. Bob, have you got a better, more informative solution?
Yeah, I've got an extremely good one here. It's one where the student uses the format given in the unit, and that means that at each stage he's got to indicate whether he's using xn to replace an or bn. But perhaps before I go on, I ought to remind you by a little diagram of how the bisection method works. We start off with an interval a1, b1 in which we know there is a solution. Then we choose as our first approximation x1, the midpoint of that interval. Then we have to decide whether the solution lies in the right-hand or the left-hand half of the interval, and that's what we use for the next step, and so on, and we gradually home in on the root. All right, let's see how it works in practice by looking at this solution. Here's the student who's chosen x1 as 2 pi over 3 and b1 as 5 pi over 6. Remember that the function was negative at a1 and positive at b1. x1, the first approximation, is the midpoint, and the value of the function at that midpoint turns out to be minus 0.445. Well, that's clearly negative. So the function changes from negative to positive on the right-hand half of the interval. So that means that the existing midpoint must become the left-hand endpoint of the new interval. And so that's why he said xn replaces an. He also puts down what the maximum error is. It's pi over 12. That's half the length of the original interval. And now we start over again. Once again, our approximation is the midpoint of the interval. The function turns out to be negative again. So once again, xn is to replace an. Now at the same time, he's keeping a running check of the maximum possible error. He sees that after doing 2 cycles, he has a maximum possible error of 0.0655. Now, that's better than we were looking for, because the question asked for 0.1. That's in the very last line of the question. So he decides that his answer is x3, that's 2.553. And that's an extremely good answer, which I would give full marks for, 10 out of 10.
Well, we hope we've given you some helpful advice, but before we go, we'd like to give you a couple of tips. First of all, if you read through a question and don't understand what it's asking for, why not ring up your tutor counsellor for clarification? It isn't cheating.
And I suggest that when you're writing up your solution, you write them up in such detail so that when you come to revise, you'll still understand what you were trying to do.
Well, a lot of those remarks apply to that specific problem, but in fact they contain tactics that can be applied to a lot of general problems, so you'll find it helpful later on in the course. Well, that finishes block 1. Next week you'll be starting block 2, and a major part of that block is to do with graphs. So you'll be taking up a lot of the ideas that Bob and Derek have been talking about straight away. Goodbye.